Hello and welcome to this video. In this video, we'll talk about optical path, how to calculate it, reduce distance concept, and when an image is formed, the optical path remains the same and there has to be in the phase, the relationship between the path difference and the phase difference, right? So this is what we'll discuss. So let's get started. Light passes through a particular medium, it interacts with the molecules in that medium, which means that the ray of light while traveling from a medium actually becomes slower, right? And we know that the refractive index is defined as the velocity of light in vacuum divided by velocity of light in medium, and Re is always greater than 1. What it means that when a ray of light travels in a particular medium, it becomes slower, right? So if a ray of light is traveling in air or in vacuum, what you get is a bigger wavelength, but when it travels through a glass, the wavelengths become shorter because it has to go through more and more sinusoidal movement to cross the interface, right? And it is because the velocity of light in a medium is defined by frequency into the wavelength. As we know, the frequency remains same in all the medium, right? What decreases is the wavelength and hence the velocity. Now let's define something called optical path, which is very simply the refractive index of that medium into the length in that medium, right? So if the ray of light is traveling for a distance L in this medium with refractive index Nm, basically the optical path here is Nm into L, right? And it is because, suppose a ray of light is traveling in vacuum, right? So in vacuum it has to travel a distance, let's say L, right? How much time it will take for it to travel in vacuum? In vacuum it will be L divided by C, because it will travel at a speed C, right? Now if it is traveling the same distance like L in a particular medium with refractive index N or N medium, we know that it will be now travel time will be L divided by velocity in that particular medium, and velocity in that particular medium, because the frequency is going to be the same, right? So it will be Vm is going to be C by the refractive index. Okay, from here we are going to put that, and basically we are going to get Nm divided by C and L. So you can see that this time taken is more than that, right? So to account for that time difference, we basically introduce the concept of optical path NL, and we say that if the light has to travel, right, similar distance, this more distance for the same time, right, then in the vacuum basically it will be the same, right? So Nm into L is the optical path, which is the distance traveled by light in that medium, which is equivalent to the time it will take for the ray of light to travel a distance L in vacuum. Okay, and this is the length it has to travel in the medium, and it is always going to be more than L, because Nm is always greater than 1. Okay, it will get more clear when we do more examples, right? So for example, the ray of light is traveling from S to P. It is passing through different medium at a particular distance d1, d2, d3, like that, right? So here the optical path it will take, right, will be the distance d1 into n1, right? Here the optical path will be d2 into n2, and here the optical path will be distance d3 into n3, so on and so forth. And the time it will take will be again divided by c, right? So same time it will take to travel this distance in vacuum, and that will be divided by c, right? So that is the concept of optical path, and it will be used in many formulation or problems in physical optics when we go ahead in interference and all, right? So please pay attention, it's very simple. Now if you're looking at the Huygens construction, when the wave of light is coming like this, right, the wave fronts are like that and passes through a surface which has a deformation and things like that, right? The waveform will change its shape, right, accordingly, so that they are always arrive in phase, right? So this is what we observe, and hence what happens that if we have a lens here, right, and here is an object, one ray is passing through the lens here and then it is forming an image here, and one ray is passing through here and forming an image here. Now we can see this distance O, A, B, and let's say I, right, and this is, let's say, P1, P2. Now what is the optical path of this ray? It goes from O to A, okay, then a small distance AB with the refractive index of the lens N plus BI, right. In here we'll go OP1 plus P1 P2 into N plus P2I. As it happens, these two optical paths always remain same when the wave actually arrive, wavefront arrive from here to here, and they are in phase so that they can form the image, right. As it appears that this is a longer path, but you can note that within the lens it is traveling a shorter distance, right, and with this multiplication, right, with this optical path remaining the same, the image is formed. And this is because of the Fermat's principle, which says that light always travel in a path which minimizes the time it takes for it to travel from A to B, right. So from here to here it has to be the same path, right, and the optical path is same. So let's look at one problem to clarify the concept. Now the ray of light travels through series of slabs placed after one another as shown with the refractive indices and length in the figure below. Calculate how much time a ray of light will take to pass through the slabs in seconds. Okay. So here the light will start here, right? It will travel 3 centimeter here, and then here and here. So we need to find out the velocity of light here, then the velocity of light here, and the velocity of light here, and simply divide that, right? Now we know that the optical path here will be N1 into 3 centimeter, right? And we can then divide it. So there are two ways of actually doing this problem, right? So we can simply find the optical path and divide it by C, because optical path is nothing but the time, the similar time it takes for the ray of light to travel in the vacuum, right? So let's calculate the whole optical path and divide it by C. That is the first method. So N is equal to N2, right, which is 1.55 into 5 centimeter plus 1.7 into 10 centimeter, right? Roughly this is going to be our optical path. We need to write that in meters, okay? So we'll write 1.33 into 0.03 meters, okay, plus 1.55 into 0.05, 5 centimeter is 0.05 meters, 1.70 into 0.1 meters, okay. And we can simply divide it. The time taken will be optical path divided by C, and that will be divided by C will be 3 into 10 to the power 8 meter per second. And when you solve that, basically we'll arrive at 9.58 into 10 to the power minus 10 seconds, okay. Similarly, you can write the equation by calculating the velocity of light in all the medium, right? So here to here, we know that the velocity of light in a medium will be C divided by the refractive index, okay. Now C is same, right, and it is divided by 1.33, okay, in the medium 1, in the medium 2 C by 1.55, and the medium 3 C by 1.70, right. Now how much time it will take in the medium 1? That is 3 centimeters, right. So 3 centimeters is 0.03 meters divided by C into 1.33, okay. This will go up. This is our time 1 and then the time 2 This is the velocity and it is 5 centimeters. So 5 centimeter divided by c into 1.55. Okay, and then it's 10 centimeter 0.1 divided by c into 1.70. Okay, and as you can see, these two equations are same, right? So one way of finding is that we can find the time it takes for the light to travel in that medium by finding that velocity, then add them up, or we can simply find the optical path and divide it by velocity of light, which means that optical path is nothing but this. The optical path is the equivalent distance traveled by light in vacuum. Okay, so in the same time it will travel the equivalent distance, and that is given by the refractive index into the distance. Okay, refractive index has no units, right? So it is a ratio, so distance, so in meters. So this is optical path. Now let's move on. It's a small demonstration on the optical path. So here we have a tank and we have a fish, and we are watching the fish from here, right? And fish is actually at a distance L, but to our eye it will appear at a distance L dash, right? The reason for that is that the ray of light will travel slower in this thing, and when observing from outside it will appear that in the same time it is traveling this much distance, right? And this distance is called reduced distance, right? And this reduced distance is simply total L divided by the refractive index of the medium. Okay, so to the eye, this is the reduced distance the eye the ray of light has to travel, so that it appears that in the same time the light will travel in vacuum, right? So let's do a problem. Actually it will clarify a lot, right? So the refraction works on the same principle, right? So let's say we have a container made of glass with a solid bottom. Okay, so we have this container made of glass with a solid bottom of height 3 centimeter, filled with a layer of water 2 centimeter, and then we have oil for the 5 centimeter. Given the refractive index of glass is 1.5, water is 1.33, and that of oil is 1.6. To find the apparent depth of that object located at A from the bottom of the container when seen from the top. Okay. So very simply, what will be the reduced distance here? It will be 3 centimeters, right? So it will be like L1, which is 3 centimeter, divided by the refractive index N1, right? For this one, so L1 by N1, and it will be L2 by N2 and L3 by N3, and the total reduced distance will be just sum of that, right? So it will be sum of, right? So let's find that out very simply. So it arithmetically it's sort of adds up, right? So that becomes our life easier. So here the L1 is 3 centimeters, right? Divided by the refractive index is 1.5 for the glass. Then we add for the water 2 centimeters divided by 1.33. Third is 5 centimeters, and for the oil is 1.62. And when you do the sum, basically it will come to 6.56 centimeters, because all this we have kept in the centimeter. So here the reduced depth will be 6.5 centimeter from here. Okay, so finally the object will seems to appear at a 6.5 centimeter from the top, right? Always remember the reduced distance is from the top, from where we are observing. Now as I said, when you have a lens, right, and the ray of light or object is here and the image is forming here, these two rays travel the same optical path and arrive in phase to form an image, right? So in all the optical system this is true. And when you remember that when a ray of light is passing through an optical system, right, the optical path remains the same, because the light will always travel a path to minimize the time it takes to travel from A to B. Okay, so here is a point A and here is a point B, right? Whatever time it takes to travel from A to B, and if there is a glass here or something, right, and it's traveling like this and again coming at this point, right, forming an image, it will do it in such a way that these two path, such that the time taking T1 and T2 and these are equal. Okay, that is true for the lens and for other optical system as well, and that can be proved. That using that principle we can simply prove the law of reflection, right, and law of refraction, right? So there are proofs you can see of via Fermat principle. So using that, basically let's look at the next problem. Now two parallel rays at a distance d strike the prism of refractive index n as shown in the figure. After getting deflected by the prism, right, so it will get deflected by the prism, ray continue to travel in the air and meet a slab of thickness d. Okay, here's a slab of thickness d, such that one of the ray fall on the slab with refractive index n1 and the second one at the refractive index n2. So what will be the effective path difference between the ray after passing through the slab, right? So now we know that here to here in air the path difference, there is no path difference, right? So this is same. Here it is traveling a less distance, here it is traveling more distance, right? But again here it is traveling less distance and here it is traveling more distance, so that this optical path, right, the time taken to travel from here to here, as we said, will be always same, right? So there is no path difference, optical path difference happening here. So this optical path of 1 and 2, right? So optical path 1 will be always equal to 2. So that's the nature of light, right? Now where the path difference or optical path difference will come when it is sort of traveling from here to here, right? Now what will happen here, the optical path will be n1 into d and here will be n2 into d, and basically the optical path difference is going to be n1 minus n2 into d, right? And there will not be any other optical path difference here, right? Remember that. So so the answer is n1 minus n2 into d. All other information is not required. Now one thing more, when we have this optical path, right, the path difference, we can actually relate it to the phase difference. Okay, now if we have a wave, right, and this is a wavelength, it takes phase from here all the way to 360 or 2 pi, right, in one vibration, right, in one lambda. Now the path difference, so the relationship between the phase difference, how much will be the phase difference for a particular path difference, right? So here is the path difference, right? For the one phase difference change, basically it has to travel 2 pi in the phase difference and the wavelength is lambda, right? So more time it travels, the phase difference will be 2 pi by lambda into the path difference. Okay, remember that. So this is a relationship between the phase difference and the path difference, which we'll be using when we are doing interference and other physical optics. So with that I will close. What we have learned today is basically about the optical path and its importance, right? An optical path is nothing but the refractive index of the medium and the distance, right? So it is introduced to say that the ray of light traveling through the optical path takes the time t, it will take the same time t in vacuum. So this optical path is basically an equivalent path of ray of light in vacuum, right? Now with that we have solved a couple of problems using example, also related it to the phase difference, right? We found examples of optical path difference, right? And then we related it to the phase difference, and which is given by 2 pi by lambda into the path difference. So if you want more videos like that, you can go to deepdivephysics.com, register and watch all the videos in a nice playlist. We also provide one-to-one and small team guidance. So if you are interested, please get in touch and we'll help you with that. Also, don't forget to like and comment on the video. Thank you very much.